Hi everyone, welcome to our another live stream. So in this stream, what we are going to see is that what is AFL and how can we use it to fuzz a simple software. Then we will also see how can we use CDB to debug the crashes which we have found using AFL. So we are going to use a very simple C program which we have been using in all my previous videos. Just give me a minute, I will verify that everything is working fine on the streaming. So just hold on and I will just see that it's working fine and you are able to see. Okay, I think it's working fine, right? So I can see few comments. Okay, that's nice. So let's start. So what uh, we can start with is first we will see what is fuzzing, right? So if you are not sure what fuzzing is, so let me go through one of the workshop slides which I have covered at DEF CON. So if you want to go in more details, then what you can do is that you can go to my website, that is fuzzing.in, and you can find a workshop which I have delivered at DEF CON 30. So it is like 2 years old workshop, and it contains AFL. So AFL is not in active development now, but what we are going to use now is AFL++. So AFL++ is actively maintained and it has a lot of community pages, and it has a great team who is working on improving this. So they keep adding new features, they keep doing a lot of bug fixes for that. So we will be working on AFL++ in this. And if you want to know what fuzzing theory, I mean what fuzzing is and all, right, so you can go to this section, that is section 8 on my fuzzing workshop, and we will quickly cover that. So basically what fuzzing is, that it is actually a software testing technique where you send various malform inputs to the software. Now if you want to find a bug manually, right, then what you need to do is that you actually need to do manual code audit. If the code is available, then what you will do is that you will go through the code and you will see that if you can find any function like string copy or any other function like mem copy which can cause some issues in your code, which can cause some memory corruption, or which can cause some kind of issue like type confusion or integer overflow, etc. So you will manually do that. But the issue with manual bug hunting is that it actually takes a lot of time, and it's not necessary that you will always have the source code available. If source code is not available, then that's another challenge. In that case, what you need to do is that you need to disassemble that code, you need to go through the assembly code, you need to decompile that, and it's a lot of headache, right? So then also it is not possible that you will cover entire code path. So if you look at any open source software or any library, you will see that actually it contains thousands of lines of code. So you just cannot go and look at the code and keep doing manual audit. It's very time consuming thing, and sometimes it's very frustrating. So you cannot do much with that, and it's also not very productive. You just cannot keep sitting and looking at the code, and you can easily miss few things, and you just cannot cover all the scenarios. So that is why what we do is that we use fuzzing, and fuzzing is basically an automated way of bug finding, and it's actually pretty fast. So uh, what it can do is that it can cover most of the code paths. There are different types of fuzzer, like there is dumb fuzzer, there are like mutation based fuzzer, and there is like coverage guided fuzzer. So AFL, what we are going to see, it is actually a coverage guided fuzzer, and uh, what a coverage guided fuzzer means is that it will actually modify your binary, and it will at the runtime when your binary is getting executed, it can identify that what are the code paths which is getting executed, and based on that it can modify your inputs. So if it gives one input, then if it takes the code path one over here, you can see, and it continues to that code path, and it will give you output one. But if you modify input one and you create an input two, right, and then in case what will happen is that it will take code path one, and then it will change it to code path two. Suddenly it will change, it will take some different direction because of some conditions in the code, and then it will continue the code path, and it may be possible that it can either give you output two if the input is proper, it is able to process the input properly, or it will simply cause some issues and it will lead to the crash. So this is what fuzzing do. It will basically take a simple input file, it will take a simple input, it will modify it, and uh, now here comes the concept of what is mutation, right? So if you take an input file, and how do you modify that? So there are various techniques which you can use. So these techniques are like pretty common across any of the fuzzer which you can see. If you take AFL, you can take honk fuzz, you can take leaf fuzzer, right? So the thing you need to understand is that any of all of this technique, they works on binary file. So in binary file, what you can do is that you can actually change various bits and bytes, and then you can also add some random bytes. You can also remove some bytes, you can trim it down, you can combine two input files, and you can create another one, and you can do a lot of permutation and combination of this technique as well. You can also do uh, you can also add some interesting value which can cause some integer overflows or some integer underflows. So for integer overflow and underflow, what you can do is that you can give some values which are very large, like 0, 7, ff, depending on the size of the integer and size of the variable you are using. So all these are called mutation strategy, and if you take any input file, if you take any binary file, then you can start from the very beginning, and what you can do is that you can change one byte, and then you can start changing another byte, or you can change one bit and you can start changing another bits as well. So it depends on your creativity, but what AFL does is that based on the experience and based on the people who has a lot of fuzzing, right, they came up with a set of standard mutation strategies, like how do you change the inputs. So they will basically use all this common strategy which you can see it on the AFL screen. We will see all this strategy when we start our AFL fuzzer. So that is what mutation is, and how does coverage guided fuzzer actually works. So what they will do is that if fuzzer basically takes a seed input, you need to give an initial set of input which is called seed input, and it can be like a very simple file which your program can easily process. And then what your fuzzer will do is that it will instrument your program. So you need to compile your binary, you need to compile your code with AFL and all this fuzzer, so that they can actually figure out what code paths your binary is taking, and based on that they can change the input. So your fuzzer will actually run the instrumented binary, it will feed this input, and then it will check that whether it is generating a crash or it is generating a new code path. So if it is generating a crash, then that is what we want. It's a good thing. So it will save the crash. And if we find that the fuzzer is finding a new code path, then what fuzzer will do is that it will actually save this code, the newly generated file, into the input folder, and it will queue it so that it can generate more interesting code paths. So there are two actions it will do. If it's crash, it will save the crash. If it is finding a new code path, then it will queue it so that it can mutate this particular file again, and it can find another code path. So this is what a coverage guided fuzzer does in the short. And there is also a concept of basic blocks. Now when we talk about how a fuzzer actually can instrument, so there are different basic blocks. Whenever you open a binary, right, or whenever you look at the simple code, you will see that it contains a lot of different lines of code like this. And when you disassemble that, when you use any of the disassembler, you will see a lot of blocks like this. Like if you open this code in IDEA, then you will see that there is one block, then there are two blocks over here, and there is third block over here. So what these are? So these are basically basic blocks. And what a basic blocks means is that it is a continuous lines of code before a program has to make a decision. So decision means that if there is some condition, like there is some if or else condition, like in this case, if you see the continuous code blocks start from here, integer x, y, z, then we are okay, I think you cannot see my screen, just hold on. So we are over here. So in case of like continuous code block, just give me a minute, there is some issue, I need to check, hold on. Okay, so we are discussing about code blocks. So a code block is a continuous like lines of code which you can continue executing before a condition has occurred. So in this case, you can see that this integer x, y, z, and then followed by there are x is equal to 0, we are assigning some value over here, y is equal to 1, z is equal to 2. So and next line there is a if condition. So the code up to here, right, the line number 4, it will be a code block. And then when we take a condition, if we come inside this condition, this will be another code block. So this will be the second code block. And then there is a else condition. So either your code will go to this block or your code can go to this block. So one of this can be executed with a single input. A single input cannot execute both of this code block, right, because there is a if condition over here. So in this case, this will be second code block and this will be third code block. Now if we see it inside the IDA, how does it look like? So this part, if you see integer x, y, z, x0, x1, this initialization part is over here. If you see it over here, right, there is a like assembly code over here. Move x, we are moving 0 to x, then move y, we are moving 1 to y, and we are moving 2 to that over here. And then here are the if condition. So this is if condition, this is else condition, right? Here we are simply checking, right, if this thing, right, if z is greater than x over here, so this will come over here or it will come over here. It is like RVP z over here and this is x over here. So based on the condition, the code will go over here, and then in the end what it will do is that it will simply call printf over here. It's not actually mentioned in this code, but that is fine. It will call a printf, that is are the value of x, y, z. Now at the runtime, suppose you are executing this code or you are executing this code and someone asks you that figure out at this particular time which part of code is getting executed. Then there is a very simple technique. What you can do is that you can simply add a printf over here, that printf I am in first block. You will add printf over here as well, like printf I am inside a if condition, I am in the second block, and you can add a printf over here like printf and I am inside else condition over here. So whenever this printf gets printed, you know that you are inside which code block. But this is not a practical solution, right, because generally you will not have the liberty where you can actually keep checking printf statement and figure out how can we actually use it to fuzz if software. It will simply print a message. So the solution for this is that what AFL actually does is that it basically adds a function over here. A callback function will be added over here in each and every basic block over here. So when this callback gets called, it knows that okay, we are executing this particular code block. Then when it moves to another code block, that callback will again get called, and based on that it will actually figure out that which code block is getting executed. So now what it can do is that I think there are some comments over here. So hi Daniel, thank you. Which null you are talking about, I'm not sure. But anyway, uh, so we'll continue with this. If you have any question, feel free to post inside the comment section. And so this is what AFL will do. Basically, what AFL will do is that it will actually add some callback function over here, and it can figure out that okay, when we give this particular input, this code block is getting executed, and then it will create a map. So inside that map, what it will do is that it will basically take the ID of this block. So let me show if we can see. Okay, so this is the disassembled binary which we have actually compiled using AFL, and you can see that there is a callback function over here, AFL maybe log, and you can see that it is actually present inside every basic block over here. You can see that inside this basic block there is a function AFL maybe log over here as well and over here as well. And I think each of these basic block will have a unique ID. So the instruction you are seeing over here before the callback function, that is move rcx, over here you can see 3ab1h, and over here you can see move r6 2831h. So what is this x value? This x value is actually the ID of this block. So whenever this function gets called, it will actually use this ID, and based on that it can figure out that this is the basic block which is getting executed by AFL, and based on that it can figure out that if you give second input, then whether this is actually executed in the past. It will basically create a you can say a it will XOR it with previous block, and it will create a value, and that value will be unique. So whenever this callback function will gets called, right, it will check whether this exists in the map or not. If it is present inside the map, it means that this block has been executed, and if it is not present in the map, then we have a new coverage. So that is how AFL figure out that a new code coverage has been found or not using the input. So if we are getting the same code coverage, there is no point in saving that input. But if we are getting a new code coverage, it means that this value is changing. This basic block value is changing. That means that we are getting a new code coverage. So that input needs to be saved to the our input queue, and from there it will take it again, and it will mutate it, and it will actually generate new input, and we will try to see if we are getting any crash or again a new input. So that is what is called basic block and instrumentation. And now what are the steps which are involved in fuzzing? So first thing you need to do is that you actually need to collect the corpus. You also need to decide what you want to fuzz. So you need to select a target, then to collect the corpus for that. And then what generally happens is that when you collect a lot of corpus, right, it may be possible that more than one file they are generating the same code path over here. So there is no point in using them. You can basically discard that. So you need to minimize your corpus so that you remove all the duplicates from that. Then you can run your fuzzer, and then when you run the fuzzer, it will basically generate some crashes. So you need to analyze the crash. You need to use some debugging tools like GDB and all, and you need to figure out what is the root cause. And then it may also be possible that the crash file which you generated, it contains some lot of unused data. So you need to remove that. You can actually minimize the test case if you want. So these steps I generally don't do much on my side, but if you want, you can do that, because once you found the crash, you can figure out the root cause. You can report this to the vendor, and just make sure that they can actually replicate the bug. So this minimization step sometimes it helps in narrowing down the root cause. Otherwise it's fine, so you can do it, or you can skip that, and then you can do the root cause analysis. So how can you generate like corpus? So you cannot manually generate corpus. If you can generate, that is also good. But if you are fuzzing an image file, so basically all these fuzzers like AFL and all, they works well for the binary file format. And what are the like examples of binary file? You can take some image for file format, like you can fuzz bitmap file, you can fuzz JPEG file, or you can fuzz some GIF file, or multimedia files, like you can fuzz that. And because the reason is that they have a lot of headers, and if you change any value, the parsing might have some issues. You can easily find them. So this fuzzer works well for the binary file format, but this will not work well for, you can say, if you want to fuzz browser, and if you want to fuzz like HTML, then this kind of fuzzer will not work. Because if you look at any HTML page, if you look at this source code over here, right, then you can see that it contains a lot of tags like HTML head and all. Now if you use any mutation technique, and then you say, if you change this HTML, you change this h to, like, say f, it will become ftml. Now your browser will not be able to parse this, right? So this is like the mutation strategy which this fuzzer uses, which doesn't work for like fuzzing this HTML file format and all this PDF file format and all this kind of thing. This techniques work very well for binary, but this will not work well for uh, like HTML and all this, where you have a structure input. So this will not work in that case, or where you have some grammatical input. So for, if you want to fuzz HTML and all this thing, in that case what you need to do is that you need to actually use grammatical fuzzer like Domato and all this thing. So we are not covering that, but you can explore that if you want to fuzz browsers with that. And so this is what the basic theory is. I will not dwell much. I think we have like already spent half an hour on this. So let's do one thing. We'll move to the hands-on. And just 1 minute. I think I have seen some message. Just hold on. I cannot see the message actually. The screen is kind of dimmed here. So okay, so I think Abhinav has asked a question, fuzzing HTTP request. So HTTP request, no, you cannot actually fuzz with this fuzzer. I mean, if you can fuzz, it depends what kind of request you want to fuzz. So if you are like fuzzing get request, and suppose if you want to find the bugs, like if the get request contains or say the length of get request is more than 1000 bytes, right, then this kind of fuzzer are not very suitable to fuzz this kind that kind of thing. But if you are fuzzing some like say like input file, then you can use that. But fuzzing HTTP requests, I think this kind of fuzzer are not suitable for that. So let's move on. Hi Himansh, hi Abhinav, Daniel, Ravi, welcome to the live stream. So let's go ahead and see how can we install AFL++ first, right? So let me go to the AFL++ URL, AFL++, and okay, so this is the GitHub URL for AFL++. And what you need to do first is that you need to clone it on your system. So you can copy this like this, and you can type this command git clone and the URL for AFL++. Actually there is some issue with copy paste. Okay, I think this character I need to remove. Okay, so you can run this command. It is git clone and followed by AFL++ GitHub hippo URL. So on my system I already have it, but so we can simply go to AFL++. I will actually verify that it is latest or not. So we can use git pull, and it will actually update it. And meanwhile we will see if we get any install directory or install readme file over here. So that will actually help us. Okay, it should be here. Okay, we can see that. So there is a Docker image as well. If you want, you can directly download a Docker, and you don't need to go through all the compilation steps. But generally, if you are like interested in knowing how can you first you want to do some customization, then you can actually compile it manually, like what we are going to see now. So okay, so there is a install file over here. Let's go through that. The Docker version we are not going to use. What we are interested in is that how can we install it with all the dependencies. So the instructions are straightforward here. We can simply copy this entire all this uh, command. So basically what it is doing is that it is updating all your packages using sudo apt-get, and it is installing all the packages which are needed. So like build essential, python 3dev, automake, cmake, g8 flags, and everything what is required for AFL++ to work properly, it will be installed by this command. And then it will also install llvm version 14, because this is needed for Clang and some of the feature which is supported by AFL++. It will also, I think, install some standard libraries like libstd over here, and it will also install ninja build, which is actually needed for KMU mode. I think KMU mode, depending on the time, we will see, or we might skip in this broadcast. We will see it in future broadcasts. Let's see. Then it will simply clone the Git repo, which we have already done, right? And we need to go to the directory. We need to simply run the strip. So the strip will make everything. It will make basically it will add support for like KMU mode. It will add support for Frida. It will make support for Unicorn and everything. Whatever is present inside AFL++, it will basically enable that. And then you can do sudo make install. So we have already done these steps, right? We don't need to do this, and I have already installed the libraries on my system. But let me show you again and see. So okay, AFL has pulled the Git repo. I mean, we are on the latest Git version, and we can actually run this command. Just copy paste this command and run it, and it will take some time. So one more thing, the system requirement for AFL plus, right? Generally try to get a VM, because if everything, you can actually take the snapshot, and it's very comfortable. You can actually restore it if something goes wrong. And try to get 4 processor, 4 cores, and try to get minimum of 8 GB of RAM, so that you can actually run some fuzzer, some decent kind of fuzzer. But the more cores you have and the more RAM you have, it will be better. So our AFL thing is done. I think now we simply need to run this command, that is make this, right. So let's run this command and see if it works fine or not. So you will see a lot of output, lot of messages, because it will compile various tools and utilities. So we need to wait for like few seconds. It might take some time, but nothing we can do here. So let's wait. So meanwhile, if you have any questions related to fuzzing, feel free to ask. So I'm actually running a live stream on this as well, so it will take some time. Our system is kind of slow. And then we need to run this command, that is sudo make install. So what this command will do is that it will basically install all the AFL++ related tools which we can use. Okay, I think it is making camo AFL. Okay, it will take some time. Fine. Almost done, I think. Okay, it's now compiling it for like unicorn mode. So will take some more time, but anyway, I'm just trying to make sure that there is no error message over here. Okay, this is fine. This is not an error. Okay, so I saw something in the red and I thought we are getting some compilation error, but this is not an error. That is fine. Okay, seems to be good. We are good as of now. Let this compilation gets finished and then we will fuzz a simple C program. So let me actually go through that program. So I have actually created a program that is called vulnerable C program. And how I created is that when I fuzz various software, I found that the crashes which I was getting, they belong to any very few selected categories like integer overflow or integer underflow or like out of bound read and write. So I thought let's create a very simple program which we can use to show the fuzzing concepts and people can easily understand what are different types of vulnerabilities. So you can actually search for this damn vulnerable C program. You will get it on my GitHub repo, and I will quickly walk you through this. So what this program will do is that it actually has a main function. It expects one input file, and then it calls the process image function. So basically, it is a imaginary, you can say, image file, and it's try to process that image. And now that image file, right? It is a very simple file. So it will contains a header. Uh, then it will have a width, it will have a height, and it will have a data. So this is a structure which is image, and these are the different parameter which an image file will contains. And then inside this process image function, we are simply giving this input file name. It will open this input file name and it will try to read this inside this structure. So it will read header, it will read width, it will read height and data, and it will perform various operations on this data, like it will add width and height, and then it will generate one value, and it will call malloc, and it should try to see if we can allocate this buffer or not, and then it will copy some data to this newly allocated memory. So if there is an integer overflow over here, then this size actually it will become very large or it will become very small, and then when you copy some data, it will cause heap buffer overflow over here. So these are like some of the normal very common, you can say, case which I have seen in most of the like open source softwares or libraries, even in closed source. The basic logic, like whenever a crash occurred, when you debug that, you will find that something like this is happening. So this is like for integer overflow over here. Then there is a use after free as well. So we are allocating this buffer, and uh, we are freeing it over here, and then we are actually like trying to use that freed buffer. So that is a use after free, or if we are freeing it again, like here we have freed and we are again trying to free that, then it is like double free. And then there is integer underflow. It's like a reverse of integer overflow. You can actually go to my uh, workshop if you want to know more about this vulnerabilities, and if you want to see some real world example. then there is a divide by 0. So if here we are dividing image width with image height. So if you divide it by 0, then what will happen is that it will not work. Your program will show that divide by 0 error. So this is for that. Then this is like out of bound read. So if you notice over here, the buffer 3 is of 10 bytes, and if the size is more than 10 bytes, then this will be an out of bound read. And similarly, it's like out of bound write as well. So buffer 3 is like 10 bytes, and if you are trying to write which is beyond 10 bytes, this will be out of bound write. So these are simple vulnerabilities, and if you are not freeing up the memory, then this will be memory leak. And there is something called stack exhaustion, and I think heap exhaustion as well. So in case of stack exhaustion, what it is doing is that it is calling stack operation, and what it will do is that it will continuously recursively call this particular stack operation. So what will happen is that your stack memory gets filled, and then your program will display a message that stack exhaustion has occurred. And similarly in heap, you have limited heap memory, and then in that case, if you are trying to allocate memory which is very large, like FFFFFFFF, that size of memory your allocator will not allow, particularly if you are using ACN and all, right? These are not allowed, so your program will crash over here. So this is like continuously allocating a lot of memory inside heap. So this is what you call as heap exhaustion. So this is what it is, and this is a very simple program. When you fuzz it, you will get a lot of crashes which you can actually debug. So I think, okay, our EFL has compiled successfully. We can simply install it. Let's install it by typing sudo make install. So sudo make install, and this will actually install all the EFL binaries, and you can see that the installation has happened inside, I think, user local bin. So you can see various AFL based compiler over here. So these are compiler wrappers. Basically they will actually instrument your binary. It will add that instrumentation code, right? AFL maybe log, which we have seen in the start of the video. It will basically add this videos, and it will basically create a new binary. So you can actually look at output. Okay, this is where the binaries are. Okay, leave AFL. Okay, there is a compile log pass as well. There is GCC pass. Okay. Yeah, so if we simply see user local bin and AFL, user local bin, okay, we can see all this binaries over here, right? These are presents over here. AFL, let's say clang AFL, or you can call it AFL clang, AFL clang pass. Everything is present over here. So now AFL is installed, AFL plus plus is installed actually, and let's go to damn vulnerable C program, and I have the code over here. I am the read.c. This is the same code which we have seen, right? So now what we need to do is that we need to instrument it. So we will use a command that is called AFL, let's say AFL GCC or AFL clang, and we will simply compile it. We will use address sanitizer. So let's use address sanitizer so that we can easily identify the crash, and we can use undefined behavior sanitizer as well, and we will give the input file, and then output file will be img read. Let's name it as live stream, so that I identify which file is that. Okay, let's see if it works. Okay, so we can see that it has actually instrumented at 141 location, and it has generated a 64-bit binary, and it has used AFL clang, right? So our binary, if we see /img read live stream, okay, this is the binary, and we can search for the symbols. So and if you want to verify that whether it is like ASN compiled or not, we can simply search for this in img live stream, and let's grab for asm. So it's not coming, I'm not sure. Let's see all the symbol first. Okay, it's over here. Okay, we can see, okay, so it should be small. I was actually trying capital. Yeah, so we can see a lot of asm related calls over here. Similarly, we can actually use ubsen. Okay, so it makes sure that our binary is actually compiled with asn and ubsen, right? You can see shadow memory, all these calls over here. So this is actually good, and I'm not sure if I have Jidra over here. I can actually show the compiled binary as well, if it's there or not. I need to check. Just give me a minute. So we can see that what is the changes which AFL has actually made. I will just see if it's there or not. If not, then cannot do much. I doubt I have it. No, I don't think I have Zidra on my system. Anyway, I will install it later. So anyway, you can open this binary using Zidra or any of the decompiler, and you can see that you can see this AFL maybe a log. Let's search that actually. Yeah, over here. So this function is present inside our binary, right? So now we can fuzz that, and before we fuzz, we need to generate a seed corpus. So what we can do is that we can simply create a directory, make directory in, and we can create a test file, like let's say we can call img, and we can input it in.1.img. So we have this test file, and now the command which we need to use is afl fuzz dash I, our in directory, dash O, our out directory, and am is none because we are using 64-bit binary, and dash img read live stream and @@. So I will explain this command. So afl dash fuzz is the afl binary, afl plus plus binary, which will run our process. It will fuzz, it will generate all the input, and it will take care of everything. Then dash I will to give our input directory which contains like basic input file, then dash O which contains the output. So any crash which will come, it will be saved inside our directory. Also the new input which will be generated will be saved inside this out directory. And am is memory and none. So what happens is that if we use ASN and UBSN on 64-bit system, it will actually take a lot of memory, and generally your program will not run. You will get some issue that it's not able to allocate that much memory. So that's why we are using this. And dash dash, it means that the command before this is afl first command, and the commands after that, this, right, dash dash is your input file name and followed by any of the argument. Now in our case, our binary is taking one argument, so that's why we are using this @@. At the runtime, what will happen is that this afl plus plus binary, or this afl first binary over here, this will replace this @@ with the input file which it is generating. So it generates an input file with the name dot current underscore input. We will see that in output folder, and it will replace that, and it will give that as an input. So that will be the mutated file, and when you run that, it will basically pass. Our program will pass. Now suppose your program takes more argument, right? So say it takes file name, then it takes something called another argument. So you can give it over here like paste in the sequence in which it occurs. Now if your binary takes the argument is taste first, and then it takes the file name, then you have to change that location over here @@ location. Okay, so now since our binary only takes one argument, let's run it and see what happens. So okay, So we are getting this error that codum notification are going to external, so we need to run this command, which is pretty simple. We'll simply copy this command. Okay, just 1 minute. So we have copied this command. Let's do sudo I, and we will paste this command. So what it will do is that all the codum will go to core pattern, and we can exit from here. And now let's see if our fuzzing works or not. Okay, so there is some permission issue over here. This may be because of the directory. Let me try with different directory name. Okay, so yeah, so some permission issue was there, and you can see that AFL fuzz AFL plus plus, actually not fuzz is working, and we can see the screen. So let's go through the screen. Actually, the first section is process timing. So it gives you the runtime. It means that your fuzzing process is running since last 24 seconds. Then last new find, so when was the last time it found a new path. So since our program is very small, it may not be able to find that much. So you can keep a eye on here when you are fuzzing any software. Then last saved crash, so like when we saved the last crash, so it was like happened like 20 seconds before last save hang. So the concept of hang is that whenever you fuzz a program, and if your program doesn't respond in a specific time limit, then it will be marked as hang. So because fuzzer cannot wait infinitely, right? It has to move to the next input, it has to do next mutation, so it will basically mark it as hang. It will kill that process, so that you will see over here. Then cycle progress, so like it will process all the input in the queue cycle, and it will keep mutating that. So if it process finishing one all the sets in the input, it will mark it as a one cycle. Then runs timed out, so how many like timed out where it did not receive proper response. Then these are the map densities. So the map is a huge, like we have seen all the basic blocks over while we are seeing, like when we started this video. So if map, what is the uses of map over here, that will be mentioned over here, but our program is very small, so we should not be bothering about that. And over here you can see that the strategy is havoc. So what havoc strategy means, this is a mutation strategy, and what it means that just use any of the random mutation strategy, like you can use bit flip, you can use byte flip, or interesting values you can use. So it will simply select any of the random strategy, and will start using that. Then what is the stage execution? So how many input it has processed, like then there is total execution, so how many total execution your fuzzer has done. So you can see that we are getting a speed of 300 plus per second. So per second we are executing 300 plus inputs. So with that, if you count, it has executed like 54,000 execution. Then what is the fuzzing strategy yield? So these are the different fuzzing strategy, right? Or the mutation strategy, you can say. So bit flip has not yielded anything, byte flip has not yielded anything. Arithmetic, it means that it will randomly add some data, it will randomly like subtract, add, delete, multiply uh, some values from the input uh, binary or input file which is at read. Then there are known int, so there are various interesting values like 7f or 7fff or 7ffff or fff if it has resulted in any of new paths. So right now it is not used that. Then there is a dictionary, so we can also give some dictionary to AFL. Basically, say if you are fuzzing some image file like JPEG, right, then it always start with JPEG, then it might have some different header, like in case of PNG it will have a IEHDR. So if you give this dictionary, it will actually make uh, it actually helps your fuzzer to find these new paths very easily. Otherwise it will keep mutating that header value as well, like it will give IE, then it will give some random value, so you will not be able to find new path because your binary might discard those inputs. So it's always a good idea to use dictionary. And then havoc and splice, so this is the strategy which I think it is using right now, and it is resulted in like 12 new paths or crashes over here, which you can see. And you can also use your custom mutator, which has been written in Python. So we are not going to see that now. And you can also see that what is the level. So level 1 means that it is currently at the first level. If it finds a new path, it will move to the next level. If it finds another path, it will move to the level 3. So how it is like going through the code, but ours is like very simple C program, so you may not see any new level coming in over here because we don't have much function calls and all these things, so it will not be changing. And pending, so it has done all the path, and stability is 100%. Generally you won't see 100% stability. It should be varied somewhere from like 60 to 80%. It varies, like sometimes uh, you get less as well. So if it's less, then it means that there are some inputs which are generating non like you can say random paths. So if you give input one time, it will generate one path. If you give it second time, it will generate another path. So that's why this will affect stability. So this is the like uh, AFL status screen, and you can see that it gives the first file name and the default instance. So you can actually run multiple instance, and these are like I think uh, power schedulers or yeah. So this don't worry about them right now. And if you want to cancel that, you can actually simply press Ctrl C, and now you can see that it has created out1 directory over here. And if we see the structure, it created a default. So when you run multiple instance, right, it will create a directory over here for every, like you run master, so it will be master. You run slaves, it will be slave for them. So let's go and see what does default directory contains. Okay, you can see that it contains various directories and file as well. So the command line, first one is command line. If we do cat command line, you will see that it actually contains the command which we have used, right, to fuzz the program. So this will contain the command line for our like binary. So this is the command which we have used, and you can replace this with your input file. Then the crashes is actually a directory. If you go to crashes, you can see that it has saved each and every crash with a unique file name. So let's understand the file structure. So ID means it's like, what is the ID? It's 000. The signal means that when it's crash, what is the signal? It's like 06. Then source, so which is the file which it's mutated. So if you recall, right, we have given only one input file. So this is the first file 000. It's the first input file which is mutated, and uh, how much time it has taken, I think, and what is the execution and what is the operation. So what is the strategy used, and you can see that it is actually using havoc strategy over here. It is like repetition of 1 by 2 something. So you can see that you can also get info on the number of executions and the strategy, and what is actual strategy, what it has actually done over here. We generated this input file. So, and I think we can actually diff two files. So let's try diffing two files. So input 0 and input 1, they are actually differed. Yeah, so these are the different input files, and I want to see what are the actually, if you can see the binary diff. Just hold on, I need to check the command. Okay, we can use xxd. So let's see, and I need to use y. Okay, I can use dash y. Oh, it will not work, so I need to use xxd. Okay, and here is the first file, and let's try the second file. So this is the second file, hopefully it should work. Yeah, okay. So you can see that the difference is pretty obvious. In first file you see I followed by a lot of am characters, and in the second file I followed by t characters. There are a lot of difference over here, so you can actually see that these two are the different files. And that is one more thing. Let's move to the next directory. So we have seen the crashes directory. There is a fast resume.bin. You can actually resume your execution from where you stopped. For that, this file will be saved. First bitmap is the file which actually gives you like what is the bitmap for this fuzzing uh, thing. So, and further setups, I think you can ignore. It doesn't contains anything useful. Further bitmap, it will be an binary file, something like this. You can see if you open, but you don't need to check right now because it's not required. It's like kind of very initial thing for you. So let's also see if fuzzer setup contains anything. Okay, so it actually gives you the command line. You can see afl first dash I input all this thing. It will give the entire command line. It will give, and if we see the fuzzer states, let's use cat. We'll see. So it contains all the stats which we have seen in our fuzzer start time and time and whatever status screen you are seeing, right? It contains that. Hangs, we will not be able to see any hangs here, so it's fine. Plot data, we don't need to read. If we go inside queue, we will see that we only have one file which is actually the original image file which we have given. There is nothing else, so there are no, I think, new input which has been generated. And what is target hash? If we just see, so this is the hash of the, I think, our first program. Let's see what is that or something different. I think I'm not sure how they are calculating, but that anyway, that is fine. So this is how you can fuzz. And now let's try to replicate one issue. So we will use our binary, that is img read underscore live stream. Let's go to out one folder, and then we need to go to default. We'll go to crashes and let's take first input and see. So you can see that uh, we are getting address sanitizer message. It means that there is a stack buffer overflow over here. I think that should be inside printf over here. So let's move to another one. This is happening because printf uh, tries to uh, print data. So let's try with different thing. Second one is resulting in segmentation fault. Okay, so there are a couple of issues over here. So it's actually a double free over here. I think we can debug that. So we can see that we are calling free, and then there is something called uh, process image function at line 62 over here. So let's do one thing. We will actually see the code. Let's see what is there at line 62. So line 62 is a free. Okay, and there is another free over here. So we are freeing buffer1 two times, and buffer1 is allocated by size1, and size1 is calculated using image width and image height, and image width and image heights are coming from the input which we have given, right? So that is why our program is crashing, and it actually gives you more detail over here as well, that at the line 59 we have already freed this thing. So that is right. So this is first free, and then there is second free at line 62. So you can see that there is a second free over here, and we have already freed this at line 59. So this is what is causing double free over here, and we can actually use GDB to debug this as well. I'm not sure if I have pawn tools installed. Let me install pawn tools. Okay, I think I already have it installed. If there is any GDB init or not. GDB, no, I don't have, so I need to install pondbg so that we can debug these crashes. So let's see how we can install pondbg. Let's simply copy this. Let me go to, okay, git clone. It will actually clone pondbg. That's very useful when you want to debug crashes and vulnerabilities. Let's go to pondbg and see. Okay, there is a setup, not a set script. I think we need to run that, but we'll verify once. Uh, yeah, okay, we simply need to run this setup.sh. So let's run setup.sh. And it will take some time. So meanwhile, if you have any questions, feel free to ask. Let me check. Okay, so I think PoundDBG has been installed, and GDB init, it has also been set up. I will just verify it once. Okay, and that is installed in PoundDB. Okay, that's fine. So let's move back to our damn vulnerable C program and try to debug this. So we will use a command, gdb's ux dash dash ux actually, and then we will use our file name, our program file name, and we will give the file which is crashing, right? So I think it was inside crashes and id. For some reason the autocomplete is not working. Anyway, we'll copy paste the file name. So it is id2, and let's copy paste it over here and let's run it. So we can set a breakpoint at process image. So and then we will trace it out what is happening at runtime. So we have set breakpoint, and let's run it. So you can see that we can see the registers over here, assembly over here, and source code as well. So now let's simply run, and so that we can see how the file is getting passed. Hopefully it's working. Yeah, let's click and okay, so the file will be opened here. Let's print file pointer. Okay, it's over here. So this check will pass, and we are inside while loop. So it will read into the structure img over here. So this is the structure, right? So let's print img dot width first. It is 0, and what is height? Height is also 0. So img is proper, right? Yes, data is also 0 over here, so that is fine. So let's move to next line. It will actually print, and now we can see that we are trying to calculate size 1. So size 1 will be 0 because image width and height is 0. Now when you allocate a buffer with size 0, what will happen? Let's see. So we can actually see this. So there is no buffer allocation happen because we have uh, given 0. So we can print buff1 over here, and if we uh, print the data, actually imd.data, what does it contains? So it contains 0 0 0, right? This is what data contains, and I'm not sure if we can print size of. So the size of buffer, okay, this is 8 byte, that is fine. If we move next, so it is trying to copy the data, the 10 bytes of data inside this buffer, right? So let's see what will happen over here. So it has copied the data, and then it is actually print this buffer. So right now if we print buffer, this is not just wait a minute. So since malloc is actually 0, it can return as valid pointer or null. So it is actually implementation specific, and that's why we are getting a malloc pointer over here. So we can actually, if it's a unique pointer, we can actually pass it to free. So that is why we are trying to free it. It will work. Okay, so let's see. Yeah, so it has actually freed up the memory over here, and now we can print size. So size over here is 0, and if you divide it by 2, it doesn't matter, it will go inside if block again. So it will again tries to free the buffer, but we have already freed it over here. So here we will get the double free message. So let's try an over here, and we can see that asn is figuring over here for double free. We can actually see, yeah, so this is why this is crashing. So this will be the root cause. The root cause for this will be that the size of the buffer which we are allocating is actually the length of the variable over here, right? Size length is 0, and then it is actually freeing up the buffer first, and then it is freeing up the buffer for the second time as well. So that is why it is crashing. Now we can actually quit from here. So this was the root cause. Let's try running another input and see if we get any other kind of crash. So I will try with input 3, and it is also causing some floating point exception. So it is actually a division by 0. So it's simple one. Let's try another input. Okay, so it is saying that the requester's allocation size is exceeding the maximum supported size. So this is because of SN, and this is because the size has over here, right? It is very big, so it's at line 86. So let's directly debug it. I will actually copy paste this and we'll pass it to the GDB. So let's run gdb dash dash args / img read live stream, and then we will give this argument, and again we will set a breakpoint on main r so that we can run. We broke on the main. Let's continue. We will exit this AFL maybe log function, and over here inside process image. Okay, I did not stepped in, so let's restart. Okay, we'll run it again. Control CNN. Let's break a process image actually and run. Okay, let me restart. Actually, it's not working. So we will break it. Process image function, and we will run it. And AFL maybe log anyway. We want to skip that. So let's wait till it returns. Okay, and now we will use an. It has read the file. It has read the structure, and here we can actually print. So print img width. So this is the width, and if we print it, it's in hex. It will be this one, like I1, F3, F2, F2, and let's print height as well. So it is F2, 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 and 0D. So now let's see what is the value of the size variable. So okay, now let's print size 1. So it is actually very large, which is 44E6 E4FF. So let's see if malloc can allocate or not. Let's print let's do an, and it is able to allocate. Okay, so this check was successful. Now let's see the value of size. So size 2 actually over here. So I think this might crash here. It is actually optimized out. Okay, now let's print size 3. So you can see that size 3 is actually a negative value over here. So negative when you pass to malloc, what will happen? It means that malloc actually takes unsigned int, right? So signed to unsigned conversation, if we see converter, yeah. So here if we give -6, and hexadecimal, let's try something different. Okay, it will become 0. No, this is not unsigned long we want. Okay, unsigned integer. Yes, over here it will be actually same. I'm not getting this over here. Let's do one more thing. Signed to unsigned conversation. I want to see the size actually. I think we can use cyber chef on dbg. We don't need this. Also, we don't need. So I am not sure if it gives unsigned or signed thing. Anyway, let's try with GDB. So we can see that the size is size 3 over here is -6, right? And it will go to malloc. I think we can print this. Let's print it in the hex. Yeah, it's simple actually. Yeah, okay. So this is very simple. You can see that the size 3, which is a negative number, when we convert it to hex, it actually becomes FFFFFFA. So this is actually a very big number for malloc, right? You cannot malloc for this size. So it will crash over here. So let's do n, and yeah. So the reason or the root cause is that it is an issue with the signed to unsigned conversation, because in the signed we are giving a negative number to size 3. We are not checking it over here, and we are passing it directly to the malloc. And when you pass a negative value to malloc, since it is unsigned, malloc will treat it as a very big number. Malloc doesn't understand what is signed, what is unsigned, so it will try to allocate this much memory, which is very large, and the maximum memory size which can be allocated by our program is this one. And what this is requesting is this one. So this will not be allowed, and that's why SN will cause this crash. So this was the root cause of our second crash. So you can see different crashes actually. What you can do is that you can go ahead, compile this program, configure AFL++ on your system, and when you get crashes, you can try debugging that. So let's see if I can find any other types of crash. No, I think most of these crashes are because of allocation size, and we already know the root cause. There is one more segmentation fault, but I think let's not spend much time on debugging this. I think you know how to install AFL++ on your system. How can you compile simple C program, and how can you actually debug the crashes? This is a very basic session, but I hope that it has given you a good idea. Let's do one thing. We can actually see how can we run multiple instances. So right now we are only running one AFL instance, right? We have actually run one AFL instance, but if you have multiple cores, why not run multiple instances? So that will actually help you to find crashes in a very short time. So for that we can use a utility called AFL.cpu, and what it will do is that it will give you the number of CPUs which your system has. So I think on my system I have 14 cores. I think I have 14 cores, and I can run like at least 10 AFL instance on my system. So let's see how can we run. So it's actually pretty simple with AFL fuzz. What you can do is that you can give an option. You need to run one master, so you will use capital M, one master, and the rest of the command will be same. So it will run one AFL master instance, and if you want to run server slave, you can use -s and it will run slave, and you can run like one master and rest of the slave. So in my case, I want to run say 10 AFL instance, then I will have one master instance and 9 slave instance. So you can use a screen. If you don't have screen on Linux, you can configure it. So screen as, let's create a new master screen over here. I think there is some questions. Let me answer that. Can you share exam CV in open source software and how you found it? So I found a lot of CVs in various open source software. Like I first TCP dump using same approach, and I found a lot of that. But let's not cover this because this was supposed to be a very beginner section, and probably in future videos I can cover that. Or you can do one thing, you can actually go to my YouTube channel, and I have already created a video on how to fuzz various software like TCP dump or FFmpeg or a few other softwares. I think it should be there. First TCP dump, let me share that if possible. Yeah, it's there. So you can basically Google for this first TCP dump with AFL on Linux, and that will give you the approach I have taken. And if you go to my channel, I think I have covered few more software like FFmpeg and all. So you can basically go to my channel and you can see, or I will try to see if I can set up a live stream for that. So there is some permission issue, but anyway, we can run screen. Let me debug why it's coming. It should not come actually. Just give me a moment. Okay, so some permission issue is there. Chmod 777 run screen. Okay, now I think this should work. So okay, so we can see it was a permission issue, and let's run one master instance. So we will use -n and it should work. Yes, it's working, and you can press Ctrl A, Ctrl D, and let's run another screen instance for slave. So let's run it. We have another screen instance, and then again we will use the same command. We just need to change the time to S, capital S, and slave 1 to, let's say, S1. So you can see that it has found a lot of crashes immediately, right? Previously, if you recall, it only found like 12 crashes. So I think generally when you run slave instance, it will simply use havoc strategy. It will not use like bit flip or byte flip. And we can press Ctrl A, Ctrl D, and then we can again run another slave instance. Let's say slave 2. We are running screen, and then we will run the same fuzzer command, afl fuzz -s, and let's use S2 for this. So now let's see how many instances we are running. So for that we can use a utility called afl WhatsApp, and then we need to give out one directory over here. So you can see that it gives you the states, right? Because you cannot just simply keep opening all the screen window and keep checking status for each and every instance you are running. So you can use this tool, afl WhatsApp, and you can give the output directory over here. So you can see that for our first instance, the master one. It gives the stats that how many crashes, last crashes are there, and how many crashes which it has saved. So there total there are like 11 crashes for second. I think it has not found any crash. For third, it has found. Uh, how much? No crashes. Like so. This is how you can uh, use this tool and come to speed. So it will give you the total speed, total average speed, like what is the average speed per fuzzer, what is the cumulative speed, the total crashes. I think it is taking it from the wrong directory. Yeah, I think I need to uh, delete this default, otherwise. Okay, and now if we run this command, it should give us exact this thing. Yeah, so now it is giving the proper output. I think so, yes. So if you want to go and see the status, you can use screen, uh, let's say dr and master. It will give you the crashes and all this thing. So we can cancel this and we can exit the screen. Now let's use same for slave 1, slave 2. We are canceling our first process. So and then exit, and then screen dr screen 2. So we can exit. So this is how I think you can use AFL++ to fuzz a simple program, and we will see how can we fuzz various open source software in future live streams. I hope this has given you a good understanding, good idea. So let me stop this streaming. We'll move to another window. So I hope that you have learned something from this video. Please feel free to ask any questions you have in the comment section. You can also DM me on Twitter, and uh, uh, please subscribe, like, and share my channel. Hopefully that will give you more uh, info. It will help me to create more such videos. So thank you for joining today, and hope to see you in next stream. Goodbye and thank you. Enjoy your day. Bye.